finally start doing some calculations as we look at chemical analyses. First thing we want to think about is percent composition, right? This is the mass of each of the elements in a compound as a percentage of the total mass, right? So it's given by this equation, right? The mass of an element divided by the total mass times 100 as a percentage. So here's an example, formaldehyde, right? CH2O has a formula. Well, I just said that. What is the percent composition by element? Okay. The first thing we want to know is what is the mass, the total mass of, we could do this by molecule, right? Or we could do it by mole because those are proportional. So I'm going to do this by mole. And so how do I find the mass of a mole of anything, right? It's on the periodic table if it's an element. So let's see, C, I have one of those, and its mass is 12.01 grams. I have an H, I have two of those, 1.008 grams from the periodic table. O is 1 times 16.00 grams. All right, and I get then 12.01 grams of C, 2.016 grams of H, 16.00 grams of oxygen. And if I add that up, I'm going to get 30.03 grams of formaldehyde. All right, now to calculate the percentage, I have to take the amount that each element contributes divided by the total. So 12.01 grams for carbon divided by 30.03 grams times 100 will be the percent for carbon. 2.016 grams divided by 30.03 grams times 100 will be the percentage of hydrogen, and 16.00 grams divided by 30.03 grams times 100 is the percentage of oxygen. So let's see, 12.01 divided by 30.03, I get 0.0399 times 100, 39.99%. 2.016 divided by 30.03 is times 100, 6.713% hydrogen. And for oxygen, 16 divided by 30.03 is 53.28%. Oh, so what is the percent composition by element? Those are the answers. We've done it. Right? Now, one thing we want to do, let's just check and add them up just for fun. So what's 39.99% plus 6.713% plus 53.28%? I get 99.983%. It's pretty close to 100, but it's not 100. And why isn't it? It has to do with the rounding that we've done, right? So if it adds up close, we're in the ballpark. That's good. All right, so we are able to calculate the percent mass of any element in the total using this technique. Let's see, what else can we do here? Oh, we just did that. Empirical formulas, remember, this is the simplest whole number ratio of atoms in a compound, and it can be determined from the mass percent. So we're going to determine the empirical formula from mass percents. So we're kind of going the opposite way now. Remember mass percents, so like C6H12O6, that's glucose, can be reduced to CH2O. Hydrogen peroxide is H2O2, can be reduced to HO. So these are the empirical formulas. These are the molecular formulas. What's the empirical formula of water? It's the same thing, right? So in some cases, the empirical formula is the molecular formula. But what we know is that the actual molecular formula is some multiple of the empirical formula, right? This one's times 2. These ones both happen to be times 2, but you could be times 3, right? Okay, so let's do this. So the way I approach this problem is, first, let's assume, step 1, assume percentage is grams, right? If this is a mass percent, what this means is, right, this adds up to 100%. Let's just say it's 100 grams. If it's 100 grams, then the mass of potassium is going to be 24.75 grams K. Manganese will be 34.77 grams manganese. And oxygen is going to be 40.51 grams of oxygen. Then what I'm going to do is I'm going to turn it into moles. So how do I go from grams to mole, right? Divide by grams because I want them to cancel, and put moles on top. The relationship will be 1 gram equals, 1 mole equals whatever the molar mass is from the periodic table. So 1 mole of K is potassium 39.10. I'm going to use grams of K. Manganese is going to be 1 mole of Mn. So the mass is, hard to see, 50. What is that, 54.94? Yeah, okay, 55. Well, wrong, bad work by me. 54.9. Golly. 5, I'm going with 5 grams. And 1 mole of O is 16.00 grams. Whew. Okay. If I do this, right, grams calcium cancels grams calciums, and I'll be left in moles calcium. This is true for all the other guys. So let's mash these in. 24.75 divided by 39.10. 6329. So I'm going to go to 0.6330 moles K. All right, for manganese, I get 0.6329 moles Mn. And for oxygen, I get 2.532 moles O. All right, so this is the molar relationship of these guys. I could write, if I wanted to, it'd be strange, but I could write this. I could say K, and I have 0.6330 Ks, and Mn, I have 0.6329, and O, I have 2.532, right? But that would be strange because we want those to be whole numbers. What I'm going to do, though, is I'm going to divide these guys by the smallest one and find the ratio. I'm going to get, in this case, it looks like K and Mn are going to be 1. So let me do that. I'm going to divide by the smallest one, so 0.6329 divided by 0.6329 divided by 0.6329. And this one is 9998. This one is 1.000, right, exactly 1. And this one is 4.000. All right, so this guy's going to be 1. And what do we see now? That the ratio is really K1, Mn, 1, O, 4. So this is the empirical formula based on this mass. All right, so what we did, it was 3 steps. We assumed grams, we converted to moles, and step 3, we divided by the smallest. All right, so this is how we can go from mass percents to an empirical formula. All right, convert to moles first, divide by the smallest one to get a whole number ratio, right? We could report this, but it's just strange. By dividing by the smallest one, we turn this to a 1, we turn this to a 1, and we turn this to a 4, and that's how we get our empirical formula. One thing you want to remember here is don't round too much, right? Keep as many decimal places as appropriate, because we'll see some examples where if you round too much, you'll mess it up. So just do what I say. All right, next. What is the empirical formula for the compound containing the following mass percents? What you should do is pause me and do your best to do it. And then we'll reconvene. All right, remember the steps are assume grams, convert to moles, divide by the smallest. All right, I'm going to write it out. If I was taking a test, I wouldn't write this step, but 8 grams. I'm really bad at writing this. 55.40 grams. Okay, convert to moles. So 1 mole C, 0.01 grams. 1 mole H, 1.008 grams. 1 mole O, 16.00 grams. Equals, and it looks like I get 3.407 grams C. 4.54. Wow, man, I'm messing this up. Moles of H, and then O is 3.406 moles. Oh, all right, I think I'm getting this. All right, so step 2. First, step 1, convert to grams. Step 2, convert to moles. Step 3, convert to whole numbers by dividing by the smallest one. So the smallest is going to be 3.406. 3.406. 3.406. We can tell that this guy's going to be 1, right? It's not going to be exactly 1, but so close that we think we get it. This middle guy is going to be interesting, though. Punch it in. 4.54 divided by 3.406. I get 1.3329. All right. So we could just round this. We could say, oh, that's close enough to 1. But one thing we want to watch out for here is that some multiples like 0.25, 0.33, 0.50, if we retain enough decimal places and the precision is good enough, it could just be that my whole number is bigger than that. So if I multiply this by 4, I get 1. Multiply this by 3, I get 1. Multiply this by 2, I get 1. So watch out for these, because what I think I need to do here is multiply all 3 of these by 3. So it's going to be 3 to 4 to 3, because 1.33 times 3 is 4. All right, and so the empirical formula I just calculated was C3H4O3. All right, so this is the empirical formula. All right. Okay, so again, watch out for, I'll go back. Watch out for these ratios, right? Because you could be multiplying by something, right? If I round that too much, I'm going to lose that information, so don't overround. Let's just think about this. So the empirical formula is this. So I can multiply 2 by 2, and this could be a molecular formula. I could multiply by 3, and I could get this as my molecular formula, right? Or multiply by 4, et cetera, et cetera, et cetera, right? Because we know the empirical formula is a reduced form. The molecular formula must be some multiple of that. In this problem, we're given the molar mass of the compound, right? So it's just given to you. I'm going to show you how it's figured out, but in a problem that you're doing this, you're just told what it is. If the molar mass is 176 grams per mole, then we can figure out which of these multiples is true. So what I'm going to do is I'm just going to add up the molar mass of this guy. Let's see. 3 times 12.01 from the periodic table plus 4 times 1.008. We're doing the same thing we did with water and sodium chloride, plus 3 times 16. I get this guy's molar mass is 88.06 grams per mole. All right, so if this is the molar mass of the empirical formula, right, what would the mass of the multiple of 2 be? Times 2 would be 176. I think this is going to be important. What would happen if it was times 3? 88.06 times 3, it would be 264 grams per mole. Okay, and so what we can see then is, based on this molar mass for the molecular, or for the actual molecule, we can tell that the actual molecular formula is this. All right, so we were able to calculate the empirical formula like we've been doing, right? Step 1, convert to grams. Step 2, convert to moles. Step 3, divide by the smallest. Now we have like step 3.5, right, where we had to look and see, can we multiply it? So we call that step 4, just like step 3b. Right. Then we've calculated the empirical formula. Next, if you're given the molecular formula, and you have to be given it somehow, then you're able to figure out how many times does the mass of the empirical formula go into that. And that told me in this case that this is the molecular formula. Easy. All right. And how do they get the molecular formula? Well, we use mass spectra again, right? So remember the mass spectrometer? You excite these molecules, you accelerate them, and then you put them through a magnetic field, and they're deflected, right? The smaller ones are deflected the most, the bigger ones are deflected the least, and from that, you're able to put them in order. So here are the three isotopes of neon: neon 20, neon 21, and neon 22. All right, here's another example of a mass spectrum. This is the one we're interested in. This is our molar mass of 176 grams per mole that we saw. Right, it's really master charge is what we're doing, but for us, we're interested in the mass per mole. And then what you get is some fragmentation products that we're not really interested in here. But in organic chemistry, you start talking about this. All right, so I can take mass percent and turn it into molecular formulas if I know the molar mass.